Let's take a look at number 39. The decomposition of hydrogen peroxide was studied and the following data was obtained. We have time and concentration. So I know this is an integrated rate law problem because when we graph time and concentration, we get one slope, concentration over time. And then when we graph the inverse of concentration, 1 over time, versus the log of concentration over time, the graph with the straightest line indicates the order of the reaction. If the first one was straight, that would be first order. The second one would be, zero order, second order, and first order, respectively. All right, so what are the questions here? Determine the rate law. The word rate law means differential, so we simply write y equals k times concentration to the n. The integrated rate law. The rate law integrated is based on n. So we had to look at the graphs. We had to see which one had the straightest line. Based on the r square value, this one is closest to 1. So therefore, this is the straightest line. The graph of the log of the concentration. That is the first order relationship. So we know that it is first order, and on our equations list, this is the integrated rate law for a first order reaction. The value of the rate constant K. Again, look at your equations list. It says that the slope equals negative K. The slope is given. So therefore, K must equal the negative slope. So we just take the slope and put a negative sign in front. And so K is this positive value, right? Because two negatives make a positive. The next thing we have to find is the concentration at 4,000 seconds after the reaction starts. So back to our equations list. Which equation can we use that'll give us the concentration after 4,000 seconds? It's this one. The concentration, we know K, 4,000 seconds, and we can find the initial concentration, right, A naught, from the table. You see, at time 0, the concentration is 1. That is the initial concentration, A naught. So let's plug it in. Concentration, K, we simply plug it in. I put it in scientific notation just so it doesn't look so clumsy. So 8.3 times 10 to the negative 4. The equation actually had a negative symbol, so that's why there's a negative symbol there. I understand that K is actually positive here. Plug in my 4,000, log, and the A naught value. By the way, the units for K, I forgot about telling you that. This is kind of weird, but if we look back at the graph, this had the log of the concentration and this had time. So the slope of that graph, these units would go away when you log them. You can't log units technically, so when you do log units, they disappear. So there's no units on the rise, and then the run is seconds. So that's why the units here are per seconds. It's the standard unit for a first order reaction if you're memorizing the ones from the notes. Okay, let's go back to our equation. So the log of 1 is 0, and again, those units go away, so this value is gone. Then I just multiply these two, seconds and seconds, so those units go away totally. Now, I have the log of the concentration being equal to this number. I have to now use the inverse log, the opposite of the log. On your calculator, you have to hit the second button and then the ln, the natural log button. So ln is the natural log, but the inverse, the opposite of that, is the function that is above that button. So when you hit second on your calculator and then you hit ln, a little symbol like this should pop up. It's a lowercase e with a little caret because this is the opposite of the log. So you're taking the opposite of the log of the concentration. So that will just be the concentration. And we'll do the same thing on the right side. We'll take the inverse log of this value and we'll get our answer. Unfortunately, the units here don't carry through as beautifully, but we know concentration must be